this is Calculus 12, Chapter 5.4, and nothing says important like fundamental theorem. So we're doing the fundamental theorem of calculus. And we're calling this Theorem 4, and it's the fundamental theorem of calculus, Part 1. So if f is a continuous function on a to b, then the function capital F of x equals the integral from a to x, f of t dt. Has a derivative at every point x in the interval a to b, and that's a closed interval. And if we take the derivative of f with respect to x, this is d dx, integral from a to x, f of t dt, and this is just equal to f of x. Now, this might look simplistic, that we just get our same function back and replacing it with an x, but it's a very long proof and it's difficult to understand, and you want to just try to understand the theorem first before going through the proof.
This is important.
And this second equation states that integration and differentiation are inverses of each other, and this is a very important statement. So we've done derivatives, and now we can go backwards and get our original function back. So let's take a look at part 1 anyways. Y is equal to integral from x squared to x cubed cos of 2t dt. Okay, so the derivative, dy dx equals d dx, and it's best just to substitute before trying to do any algebra. Okay, so we're going to do this, cos 2t dt minus integral from 0 to x squared cos 2t dt and bracket. Okay, now we can do our substitution into this formula. So we have cos 2x cubed. So we don't really want to have an x in here. We want t's in here and x's out here. That way when we substitute, we don't confuse the two. If this was an x, you'd confuse it with that x, and your substitution might go poorly. So we're doing 2t, we're substituting this x cubed for t. And because this is not just a plain x, we have to do the chain rule. So we're doing d dx of x cubed minus cos 2, and we're substituting x squared for t this time. And we have to do the derivative again, d dx x squared. And this is using the fundamental theorem of calculus, part 1, twice. And now we can simplify. So we're going to do the derivative and put it out front, because we want the polynomial terms to come before the trig terms. So the derivative of this is 3x squared, and we have cos 2x cubed. Again, take the derivative, put it out front, that's 2x cos 2x squared. And we're done. And let's look at this one. dy dx equals d dx integral 0 to cos x t squared dt. And because this is in the bottom, I'm actually doing the order property and negating it. So we're going from 0 to sine x rather than sine x to 0 with a plus. We use the order property to reverse the limits of integration and put a negative sign out front. T squared dt. Okay, and now we can substitute. We're doing t squared, and t is going to be cos x. So we have cos squared x. And now we have to do the derivative of cos x minus, we're substituting sine x for t, so we have sine squared x. And we have to do the derivative of sine x. So the derivative of cos x is negative sine x, and we always put sine before cosine. So negative sine x cos squared x. And the derivative of sine x is cos x, so we're going to put that after sine squared x. So negative sine squared x cos x. And that problem's finished. Okay. Fundamental Theorem of Calculus Part 2. And it's a mouthful, so you can always abbreviate FTC and say FTC. Now, if f is continuous at every point of the closed interval a to b, and capital F is any antiderivative of f on a to b, then the integral from a to b of f of x dx equals f of b minus f of a. And that's a very short statement, but a very powerful statement. Okay? And this part of the fundamental theorem of calculus is also called the integral evaluation theorem. Although not many people use this. More people use fundamental theorem of calculus.
This is important.
Okay, so again, this theorem allows us to compute the definite integral without Riemann sums or calculating areas, and that's very important. So if we looked at the antiderivatives, we had f of b minus f of a, and recall that f of b is some function plus c, and we have some function of f of a plus c, and these c's cancel out. So that's one way to think about this fundamental theorem of calculus. Okay, so the integral from 0 to pi of sine x dx, we have the antiderivative as negative cos x, and we're evaluating from 0 to pi. So negative cos pi minus negative cos 0. So this is minus negative 1, and this is going to be plus. Cos of 0 is 1. Two negatives make a positive. So we have 1 plus 1, that's 2. Okay, let's look at another one. This is a little harder to integrate, but when we see something like this, we should try to factor. So integral from 0 to 5, and we have 3 plus x, 3 minus x, all over 3, factor 3 out, x minus 3. Okay, we can cancel these two out. They differ by a negative sign. So we put a negative sign out front. And I gotta remember my syntax here. You need a dx. We should also note we have an NPV, x equals 3. Okay, so this problem is really quick. So, definite integral does not exist because we do not have a continuous interval. There's an NPV. Okay, so since that doesn't work, let's try an integral that will work. So we'll make it go from -1 to 2, 9 minus x squared over 3x minus 9 dx. And we've already calculated that. So we'll say integral from -1 to 2 of -3 plus x over 3 dx. And the antiderivative, we have 3 divided by 3, that's -1. So we have -x and -x over 3. So -x squared over 6. And we're going to evaluate this from -1 to 2. So we get -2 minus 4 over 6 minus -1 and minus -1 squared, that's 1 over 6. Here we have 3 negative signs, so it's -1. We have -2, so that's -3. We have -4 over 6. We have 1, 2 negative signs, so that's positive 1/6. So we have -1/2. So we have -7 over 2. And we can verify this on the calculator. So we have 9 in a bracket, 9 minus x squared divided by 3x minus 9. Draw, and we'll integrate this. F3, and we're going from -1 to 2. And we get -3.5, which is -7 over 2. That verifies the answer. And we'll add a couple of integration formulas for you. If we're integrating xn dx, that integral is x to the power of n plus 1 over n plus 1 plus c. If we integrate a dx, so just a constant value, we have ax plus c. And again, if we're doing definite integrals, we can leave out the plus c because we're already subtracting another value. And that completes this lesson.